For those of you on Zoom, I'm passing out the thing I emailed out yesterday, which is a description and list of various paradoxes that you are supposed to present on in a group of one or two. I encourage you to work together, but I just thought, for people who are at home, it may not be as easy, but you might be able to work it out that you can do it. For those of you presenting remotely, you can just do the presentation by sharing your screen on Zoom. So, I'm not going to go through in detail the stuff that's on the first page, but once you get down to the bottom of the first page and various pages thereafter, there are lots of what are called apparent paradoxes, or people refer to them as paradoxes, but there's nothing paradoxical about them at all. They appear paradoxical because some sort of misapplication of the theory of relativity is being assumed, but that doesn't mean it's easy to recognize those, even if you've spent quite a bit of time wrestling with them. And some of these paradoxes, or similar such ones, were actually argued over very strongly by important scientists early in the days of relativity. So don't think of them, even though some of them are phrased in kind of outlandish terms, don't think of them as something that's just ridiculous and made up for you in this class. Some of these are quite famous apparent paradoxes. So look through them. You're supposed to choose one of them. A couple of them have two parts, but it looks like not much of them. Paradox number 7 kind of has two different versions of it. So I would consider that to be a paradox pair. And only one group or person should sign up for one paradox. So once you read through them and digest them, if you're really excited about one of them, let me know. I'll try to come up with some sort of method of signing up, not only for a date of the first presentation, but also for which paradox you would like. And perhaps the dates will sign up on a doodle poll. Maybe you've done that before. And the idea is, last time I taught the course, we did very similar paradoxes. I've added and subtracted a couple of them in this iteration. But since we just did one presentation, it was often a surprise to me that the group that was presenting on it didn't ask for help. I'm always available for help, consulting, running ideas by me, but some people just avoid that despite all my urgings. And then they would present, and there was some misunderstanding about how to resolve the paradox. And so I want to make sure that that doesn't happen. And so the idea is, I want you to think about it, do your best job to figure out how to think about it, and I'm happy to discuss your paradox with you and your partner, even ahead of the first presentation. But I'm imagining that we will do just a first run sometime next week. That seems soon, but the end of the semester is soon too. And so I would like to have a chance to repeat after that. So sometime next week, I haven't pinned it down yet, we will do just a first run through, and you don't have to have that much. It's supposed to be a 10-minute presentation. 5 is almost impossibly short as a time for a presentation. 10 minutes is enough that you can, the idea is I want you to set up the paradox to make it seem as plausible as possible to all of us in the audience, so that when we're hearing your setup, we're sucked right into it. Don't give us any hints as to how to think about it at the beginning. Really make it seem like there's no way out of this. We've proved relativity wrong. There's an internal contradiction. How could it possibly be like this? And then carefully explain using the principles, constancy of the speed of light, or our 3 big effects, length contraction, time dilation, relativity of simultaneity, and that kind of stuff, to explain your way out of it. And I think you've probably noticed I'm a very visual person. I think it's easier to digest things, as you can see from the slide that's up right now. I really like pictures. I think pictures are worth 1,000 words, and you really come away with something with pictures. So if you can develop your, you don't need that many slides. And I'm not going to force you to use slides. If you want to present something by drawing pictures on the board because that's what you're comfortable with, that's fine as well. But I do really appreciate pictorial representations of things, and I think they just make difficult concepts easier to digest. I may have forgotten some important details. Anybody have any questions about this right now?
When will you be emailing out the link for signups?
I don't know, but ideally this afternoon. I know I've also got to email out links for advising meetings with my advisees, so that's another thing on my list. Certainly after Dr. Katavid's class, but hopefully I could do it this afternoon. I would hope at the latest by tomorrow. So, if you're really keen on one, just keep an eye on your email, and if you want to grab that particular paradox, that's fine. They're all good in their own way. Now, that doesn't mean they're all equally easy. There are a couple that are a little bit trickier, and if you choose one of those, I will sort of give you a warning ahead of time in case you want to change your mind. But I really, if you want to sink your teeth into something, a couple of them, can really be challenging to think about. Some of them are just more straightforward applications of the things that we've covered so far in this course. I also said, I think in the preamble text there, that paradox number 3, I think. Yes, the one with the super long scissors, that image there with the super long scissors. That one is supposed to be paradoxical based on something we haven't talked about yet, which is the fact that there is something bad about the ability to send faster than light signals. If you can send faster than light signals, and we won't get to this until chapter, I think, 16, which seems far away, but you're going to see we probably get through another 4 chapters today, because I'm going to tell you, once we get through this detour material, I'm just going to sort of hop through a couple of salient items in a few of the chapters that you've already read, and we're going to dig in again in chapter 13. If you can send a signal faster than the speed of light, there's a way to show that you can actually send a signal backwards in time. And there's a reason to be worried about that, because if you can send a signal backwards in time, you could send a signal to someone that could potentially say, kill someone which is, ancestor of me, and then why am I here? And all sorts of logical problems follow from that. So there's an additional postulate or assumption of the special theory of relativity, which is usually that no faster than light signals can be sent. And that includes someone traveling faster than the speed of light, but even signals made of non-human, non-sentient kinds of things, you can't do that. We'll get there, even though it seems far away now. Other questions? Should be turning in that chapter 7 homework today, and you're welcome to ask questions afterwards. I have a meeting with Muchiri at 11:55, I think. So we'll have to make sure we watch the time so I don't stay too late, but I'm happy to discuss those after class. I've got several of them from people who are remote, so that's good.
Will you be posting those solutions today?
Yes, I will try to post them as soon as I'm done with class.
Which chapters will be on the exam?
It's covering through chapter 7. The heaviest coverage is 5, 6, and 7. So we've been sort of coasting with those for a while, but that's not to say it's easy, especially when they're all thrown together in a jumble, as you found out from the homework that you've been working on in chapter 7. When there's no indication of what the correct effect to use is, sometimes it can be kind of difficult to sort out which way to go. But if you understand the homework reasonably well in retrospect, you'll be fine on the exam. If you're not familiar with the homework, then it will probably be a very difficult exam. Okay, let me try my luck here. Oh, good, I've got my pointer is working, at least at the beginning of today. Okay, I apologize, and today is going to be one last time of, unfortunately, I don't have a worksheet, so I'm going to do a little bit of review of what we talked about, And then we'll talk about some of those interesting effects like wormholes and expanding space-time and all that kind of stuff. And then we'll get into a kind of summary of the next few chapters that you've been reading in the background, which covers some things from different points of view, but are basically all on the kinds of ideas that we've already talked about in our discussion through chapter 7. We were talking yesterday about non-Euclidean geometries, and so here we're thinking of that as specifying the shape of space. And we don't care about the apparent shape when you visualize it. What we care about is the shape as experienced by a being of the same dimension who's stuck inside that space. And qualitatively, there were kind of 3 different cases for a 2-dimensional space. Unfortunately, for 3-dimensional spaces, we can't visualize them as curved because you need, just like to visualize this curved 2-dimensional surface here, I need to imagine a 3rd dimension that it's curving into. If we have a 3-dimensional space and I want to imagine it curving in some way, I need a 4th dimension, and I just can't imagine a 4th dimension. There's no way for me to sketch it in a meaningful way that makes intuitive sense. So we're going to consider analogies to 2-dimensional spaces. So space could be like the Euclidean plane, in which lots of familiar theorems hold. The circumference of a circle is 2 pi times its radius. Triangle interior angles add to 180 degrees. And the parallel postulate holds. In other words, given a line, there's only one parallel to it that can be drawn through a point that's not on the line. Those 3 things are not true in elliptic geometry. That's like the geometry of a sphere, or more generally, the geometry of an ellipsoid. It's the same kinds of things, but it's not as uniform as a sphere. It doesn't look exactly the same everywhere else if it's elliptical, ellipsoidal. But in that case, the circumference of a circle would be less than 2 pi r. The interior angles add up to something greater than 180 degrees. And the parallel postulate fails because there are no parallels through a line. And here a line means a geodesic, a great circle if you're on a sphere, in that particular case, if it's spherical. If you put a point not on the line, any line, i.e. great circle you draw, is going to intersect the one that you've already got drawn. And for hyperbolic geometry, kind of the opposite things holds. The circumference of a circle is greater than 2 pi times its radius. Interior angles add to less than 180 degrees. So you can imagine in this hyperbolic space, we were talking about this yesterday in the philosophy class, that it's pretty easy to see that this triangle, at least it looks like it has the angles that would add to less than 180 degrees. But if I shrink it down and draw a little tiny triangle right in the middle, its angles would be very close to 180 degrees. So as you inflate that triangle, make it bigger and bigger, construct it out of bigger and bigger pieces of wood, you would find that the sum of the angles actually changes. You can build larger and larger triangles, and if you're in a hyperbolic region of space, the sum of the angles is going to change as you inflate the size of that object. Similarly, if you start off 2 objects on parallel trajectories, they're going to diverge, as opposed to on a sphere or an ellipsoidal surface, they're going to start converging if you start them off parallel to each other. Okay, and in general, we're concerned with Riemannian geometry, which might, at least in the 2-dimensional case, might have regions that are hyperbolic or elliptic or nearly flat. We looked at some examples of that, okay? And that generalized not to space, but to space-time. So we're going to be talking about a curved 4-dimensional space-time, but we're still going to visualize it as 2-dimensional because we really can't visualize anything better than that, is what we need for general relativity. Okay? When we say curved space-time, we're thinking of good old Minkowski, or what we called space-time diagrams. We always drew them as flat, right? There was an x-axis. Here we're imagining beings or motion just along one dimension. Their whole world is one-dimensional. And so the space-time diagram is 2-dimensional, and we drew it as flat. And the idea is, for Einstein's special relativity, it literally is flat, or at least that's the way we've been displaying it here. Whereas in going to general relativity, we're going to allow those diagrams to have bumps and even take on the shape of a sphere or the surface of a donut or something like that, right? So we're not talking about just space now, but space-time. And by allowing space-time to curve, we can mimic the effects of gravity. In other words, we found out here by considering the surface of a sphere, if you start off two objects at rest in this weird curved x and t axis space that they lie within the surface of the sphere, even though they start off moving, they start off at rest, they're not moving left or right along the x-axis, they end up running into each other later on. Okay, and that's because this is elliptic geometry. Things that start off parallel end up running into each other. Whereas for hyperbolic geometry, things that start off parallel, you know, the A and B were initially at rest, they end up getting farther and farther from each other instead of getting closer and closer. And that doesn't sound much like gravity. I guess before I say that, in general, again, we're not interested in these highly homogeneous kinds of space-times, but rather ones where the geometry changes from point to point. So you might say at the top of this mountain, we're talking about elliptic geometry because it kind of looks like the top of a sphere, elliptic geometry for space-time. Where the mountain is just starting down here, we're talking about hyperbolic geometry. And of course, over in this region, we'd be talking about flat geometry. Okay, and the analogous things hold for curved three-dimensional spaces, right? Just like the circumference might be greater than 2 pi r if you're in a hyperbolic space. If you're in something analogous for a curved three-dimensional space, you might find that not only could the circumference of a circle be bigger than 2 pi r, but the surface area of a sphere, which in Euclidean geometry is 4 pi r squared, would be bigger than 4 pi r squared. So they're sort of analogous things, but in higher dimensions that happen. They're just harder to visualize, or really impossible to visualize. And then at the end of class, we built up this kind of weird picture of a curved space-time, and I didn't know how else to draw it other than like curled up into a scroll kind of shape, but it's still a surface. It doesn't wrap back around on itself, but it just keeps going farther and farther around the curves of the scroll. And by thinking about how nearby objects that are released from rest, whether they get farther away from each other, that's what happens here. That means we're in a region of hyperbolic geometry of space-time. And again, we're imagining our world to be just this one-dimensional path going through the center of Earth. In here, we found out that objects released close to each other get closer as time goes on. So that's a region of elliptic geometry. And of course, as you get really far away, objects that are released at rest are pretty much going to stay at rest. So we would say that's a region of flat geometry where their distance doesn't change as time goes on. And if you kind of draw that up at the top, well, I drew something that looks like kind of a sphere here or an ellipsoid surface. We didn't display it this way, but you know, this is like going up to the neck of a wine bottle, that kind of shape of a surface. And if you're creative in your mind, you can imagine laying a Pringles potato chip and it just sitting, you know, it curving this way and then also curving around from the front to the back in the other way. So it is like that surface. It's a hyperbolic geometric region. And we already talked about how, you know, being on a cylinder is the same as being on a plane in terms of intrinsic geometry. And that's what we mean by the geometry here. So it's, you know, elliptic in the middle. And I think I've got some visuals down here. So it looks more or less like a sphere kind of in the middle. Then it looks like the neck going to the neck of a wine bottle in that region. And then as you go farther and farther away, it looks more like a cylinder, which is the same as a flat plane. Okay. Interestingly enough, we reasoned about this by reasoning about masses, because I was using, if you have any intuition about Newton's theory of gravity, you might know that, oh, the forces are going to be bigger when you're closer to Earth. The forces are smaller when you get far away from Earth. The question might be, well, what about light? Light doesn't have a mass. And so is it not affected by gravity? And Einstein says no. Up at the top here, I'm saying just like everything else, light moves in the most natural way on this surface, straight ahead along geodesics. So even though I'm not showing any light signals here, if a light signal went off in this direction, it would just go straight. It doesn't look straight to us, but it's literally straight on that surface. It's not just as straight as it can be, it is perfectly straight. And light does the same thing as everything else. So there's nothing special about any kind of signal that you send. It goes along a geodesic on the surface. That's something that Newton could never have fathomed, why something that doesn't have a mass would be affected by gravity. But if gravity is the curvature of space-time, there's no avoiding it for anything that travels in space-time. Okay, just a couple of last facts before we move on to that last section. The curvature itself, we don't want to think of as a brute fact. The early thinkers we've been wrestling with in philosophy kind of took the shape of space for granted as something that was given to them. They didn't even realize it at the beginning, but that idea of three-dimensional space just going on and being completely homogeneous, that's an assumption that's being made. In the modern sense, you might say we're assuming some kind of brute fact, that it just was given. I don't know why the shape had that space, but it does. Here in general relativity, it's not a brute fact, but it's determined together with the mass or energy distribution. I don't know that we'll get to that this term because I'm trying to cut back on the amount of material for the block term, but you've heard of E equals mc squared before, and so there's sort of an equivalence between energy and mass, and the effects of mass on the curvature of space-time are the same as the effects of energy if you use the relationship E equals mc squared. So if at a certain time you know where all the masses are, that's going to determine going forward in time how that space-time, what we would call manifold, curves going forward in time. So the curvature is not something that's just given to you, but it's determined by the mass that's inside the space. So you can't think of the mass by itself, and you can't think of the space by itself, but the space and the mass distribution within it are all correlated with each other. And general relativity, in a very complicated way, tells you how to figure out what a consistent way to have a collection of masses and the associated space-time would be. Now, small masses don't affect the curvature much. So if I have a little tiny rock, it's not like it's strongly curving space-time in this region. That's not true for a black hole or a huge star or something like that. Those do curve space-time significantly. But if you have a small mass, even a grand piano, automobile, a house, those are all small masses. They're so small on the grand scheme of things, they don't affect the curvature of space so much. So they just follow along geodesics of the shape of space-time that's determined by larger masses than them. But large masses can cause significant curvature within which the smaller masses move. And so that means as a larger mass is moving, in time, it's sort of, changing the shape of space around it, and of course, changing the shape of the space-time manifold, which is complicated to think about. So, I should say, these trajectories I'm drawing up here, the shape of this manifold here, I was assuming is determined by Earth. Now, this is completely exaggerated. Earth is still a relatively small mass and has very little effect on the curvature, but of course, it does have an effect because things orbit in circles or ellipses. They don't orbit in straight lines, and therefore it is curving space somewhat significantly. But the way I've drawn this is completely exaggerated here. So the upshot is the shape of space-time and the mass distribution within it can't be independently chosen. Unlike, we were thinking about in our Leibniz-Clark debate where we said, oh, we've got space sitting around there, and how should we put the universe of matter inside it? How should we situate it? Should we move it 5 feet to the right? The idea with this is, if you move 5 feet, everything 5 feet to the right, well, the space would all move with it because the space is determined by where the matter is. So there's no sense in asking about moving things 5 feet to the right because the space is set up around where the mass and energy is in there. In a complicated way, general relativity provides a set of partial differential equations. And if you go on in math and you find out something about partial differential equations, you'll find out they're notoriously difficult to solve, which is one of the reasons we're not addressing them in any quantitative way in here, okay? But they determine the space-time shape given certain boundary conditions, and usually that's a boundary condition at an initial time. So if I know what the shape of space is and where all the mass is right now, according to somebody's definition of now, that's a complicated question, then I can determine how those masses are going to move and how space-time will be shaped moving forward in time if I solve this set of large number of coupled partial differential equations. We're not going to do that, but that's kind of the idea behind it. Any questions on that picture before we just very briefly look at some other pictures that suggest how we might think of in the context of curved space and space-time, some of the things that we might encounter in the philosophy class. Silence. Okay, I'll assume that means it's perfectly clear. Good. So let's just hit a couple of last things. That we read about the expanding universe in Lepoidovin over the weekend. The Big Bang and Big Crunch were referred to in there. Some of these things are still evolving in the minds of people who study cosmology, so they're not settled topics. We're just going to look at the very simple models that have been around for a long time. We'll also consider, I'm sure, in the philosophy class, backward time travel and some of the movies that you're going to be watching, and hopefully I'll be watching soon. We'll deal with the interesting things that happen there. So how could that be possible? Well, we can already visualize it in some way. And then finally, the concept of wormholes at least came up last time that we were in the philosophy class, the last time we taught this. So, we read about the expanding universe. I was going to blow up a balloon with my mouth, but I thought in the age of COVID, I better bring, somebody report on me huffing into a balloon and then letting it out, spraying into the classroom. I'd better do it with a pump. So I brought in my bike pump. And here's a balloon. This balloon's going to be our universe. And these little dots on it are going to be galaxies. I'm trying to hold it close enough that people on Zoom can see. And so the idea with an expanding universe is that this white balloon is space. And space can actually expand as time goes on, right? Here we're not seeing time in this picture right here. Time is what's going to happen as this goes on, but this is just the shape of space. These are all galaxies, and they have a certain small distance from each other. Not surprisingly, as I inflate this up, the galaxies are getting farther and farther from each other. Now, this is a two-dimensional world. It's a two-dimensional world, and so the entire universe is the surface of the sphere. Those dots, hopefully you guys can see it there, are getting farther apart in a way that's not surprising at all to anyone who's blown up a balloon before. And the idea is that it's not that there's something that's forcing these galaxies. Each one of these black dots is supposed to be like a galaxy, a whole bunch of stars. They're getting farther and farther. We read about farther and farther apart as time goes on. Hubble's surprising discovery that because of the redshift, he was able to infer that if we look out in all directions and look at any galaxy, we can tell by thinking about this redshift effect that it's receding from us. Why would they all be running away from us? That seems kind of strange. And furthermore, the farther they are away from us, the faster they're receding. And the idea is, well, as I blow this up a little bit, this dot gets a little bit farther away from this adjacent dot. But if that separation is increased by 1 centimeter, then if I consider this dot to 1/3 over, those would be separated by 3 centimeters. So the rate at which it's receding is going to be 3 times as big if this space is somehow expanding as time goes on. Again, this is not a space-time picture. You have to sort of add the time element in. There's no convenient way to draw this whole picture in one space-time diagram here. Okay, I think I had some comments on here, so let me share the screen again. Yeah, so galaxies are not being pushed apart. More space simply appears between the objects, much like, going back to this picture I showed last time, you can think, Pac-Man and Mrs. Pac-Man here had a certain distance between them. And that distance isn't the same anymore, but it's not because they were pushed apart. Space just appeared between them. I mean, this is a totally made up picture, but you should imagine the same thing happening with this inflating balloon. If this is our space that we live in, and as time goes on, space is expanding, it's not like these galaxies are being pushed apart. It's just that space is sort of everywhere appearing between things, okay? Now, there's still a gravitational attraction, or we can think of that as the curvature of space-time. We can't see that in this picture because there's no time. I'm just seeing a picture of space right here. But it's sort of the same way. Don't think of them as being pushed apart, but rather space is just appearing everywhere. Important point is that there's no point in the universe that everything is expanding away. Of course, when Hubble looks out there, or looked out there at the beginning, the first time these things were observed, it looks like everything's running away from us. Hey, I feel pretty important because seems like I'm the center of the universe and everything's exploding away from me. But notice from the point of view of any one of these galaxies, all the neighboring galaxies are going to be going away from them. And so anywhere you observe from, the observation is going to be the same. And there's no center of the universe in the sense that if the entire universe is the surface of this sphere, there's no point that is at the center of all the action. The center to us is at the center of this balloon, but that's nowhere in this picture. Sometimes people call, when you're drawing a picture of a space or space-time like this, they would say, well, what's out here? It's hyperspace. People call it hyperspace. But hyperspace is just another word for nothing. There's nothing there. There's no sense to what's out here. When we're imagining expanding space-time like this, it's not expanding into anything. Okay, so there is no center point of the universe. Everything's sort of symmetric, nor is there an edge to the universe. Now, I'm not claiming that the universe is sort of like a three-dimensional analogy to a sphere, but it could be. There are cosmological models that certainly allow for that. There are also other cosmological models where the volume in space is already infinite, and it's still kind of expanding in a weird way. But in this particular case, we're imagining a finite volume of the universe. That's certainly a possibility that people consider, and the issue is still open to debate. So it's what's it expanding into? It's not expanding into anything. Space is expanding, but we shouldn't take this shape that we see too literally, because it could be a crumpled version of that sphere, and it could be becoming more crumpled as time goes on, but the inhabitants of the universe wouldn't know the difference, as we talked about a lot yesterday. The rate of expansion, according to general relativity, should slow as time goes on. So there's some funniness with what happened early on in the universe, but at least at the point in the universe we are now, according to general relativity, if this is expanding, the rate of expansion should slow. And the question is, well, at some point, does it slow to the point where it stops expanding and then it starts, getting closer and closer together as time goes on under the attraction? We can think of that as an attraction in the sense of Newton, but ultimately you can still think of it as due to the curvature of space-time associated with the masses. And so that's what leads to the idea of, if it's expanding, what's it expanding away from? What was the early history of the universe? Well, maybe there was a Big Bang. And if it later on contracts, maybe there could be a big crunch. And those were the ideas that were in Lepoidovin's text. Just to visualize that, and again, you can't really visualize this unless you reduce the dimension down to almost a ridiculous degree. So here's a picture of the entire history of the entire universe, except that in this picture of the universe, one moment in time, so time is supposed to be going through here, here's our universe. It's a circle, because that's the only way we could visualize this as a curved two-dimensional surface. So here it is at an early time, not so long after the Big Bang. It's expanding. Here it is at a later time, and here it is at a later time. So that circle, which is our universe, is getting bigger, and then later on it gets smaller because of the gravitational attraction. At some point, it hits the big crunch. Now, these models are complicated by facts. Our universe isn't so smooth and homogeneous like this. And in fact, people think if there is a big crunch, it's not going to happen all at once. People think kind of when a black hole forms, that's like part of the big crunch happening in a local region of the universe. And so every time a black hole happens, a crunch has happened there, but it hasn't happened elsewhere. So there's still other stuff coming together, and that black hole still curves space-time, and so it keeps other things crunching together. And the big crunch is just a coalescence of all these black holes somehow at the end of things. Okay, so this is a picture where, again, according to our philosophy class, there's some question whether or not you like the principle of sufficient reason. Why does time start here? Why did anything happen at all at that point? And what happens after this time right there? Well, some people have proposed that, well, maybe that's, maybe it just was going like that forever. That appeals more to some people. So here's a picture of sometimes, there's no way for us to know what happens after the big crunch or what happened before the Big Bang, because I think, was this a quote from Lepoidovin that Stephen Hawking, I think, said that our physics just breaks down. Every theory of physics we have breaks down as soon as we get close enough to the Big Bang or close enough to one of these big crunches. Lost my pointer now. So every theory of physics we have really doesn't apply right there. Just like we have no idea what happens inside a black hole. It's sort of a place where everything breaks down. We're sure the general theory of relativity doesn't apply at the center of a black hole. We just don't know how to think about what's happening at the center of the black hole, but probably there's something else happening that is governed by a theory we don't have yet. Okay, what about traveling backwards in time? We can already travel forwards in time. In fact, I'm traveling forwards in time right now. That's not so amazing. But we found out an amazing way in special relativity that we can travel forward in time, and that is by the twin paradox, right? If you want to travel forward in time relative to people on Earth, all you have to do is travel really fast to somewhere far away and then travel really fast back, and you'll be younger than those people. And that's really the only thing that traveling forward in time in a more exciting way than the way we're always doing means. It means that you experience an amount of time, but other people experience much more time, so you end up just sort of ahead of them in time without having aged as much. So what about traveling backwards in time? Well, that, of course, there's all sorts of problems associated with that, like, killing your grandmother before your mother was born or something like that. Then how did I get here? At least in the picture of flat space-time that we developed at the very beginning, Minkowski space-time, it doesn't seem like there's an obvious way to do that, in the sense that once time goes on for this person, how would I ever get something to end up at a previous time? Because even when you're moving in any given way, that just corresponds to a tilted line going forward, but it's always going upwards in time. So it doesn't seem like there's any easy way to get back in time. Although we'll find out if you can send faster than light signals, we can actually send signals backwards in time, which causes all sorts of problems. In any case, not so clear how a human being would get backwards in time here. But now if we're on a curved spacetime, and we take literally that our spacetime is the shape of the sphere, we live in a one-dimensional universe, and time is going around like this, and it's curved in this way. Hey, if you wait long enough, you come around the bottom and you're back where you started at the same time. I don't know how to think about that. That causes all sorts of problems with the way we normally think of the world. But that's one way that people might think, oh, the shape of spacetime has some weird shape like this. And if you wait long enough, you come back around. Maybe it's like the surface of the donut, and the time axis is coming up the side of the donut. Well, as soon as you loop back around, you're at the same point again. Lots of problems pointed out with that in Lepoidovin's reading. Okay, so those were pictures of space-time. Now we're going back to just a picture of space again. So there's no time in this picture. And it looks a little bit weird because there's sort of a cutaway view. Not the entire universe isn't shown here, but only this is supposed to be like a two-dimensional analog of the universe. But the idea is, here's Earth, here's Vega, a distant star, 25 light years away. Even if you could travel close to the speed of light, you'd have to spend 25, at least as assessed by Earth, years getting there. That would be a challenging, certainly with current technology, absolutely impossible for someone to survive that journey. But maybe with future technology, you could get there and not age that much on the way. In any case, the idea of a wormhole is that apparently distant locations in the universe, we said, I don't have my little piece of paper, but we said, with those Pac-Man creatures, when we had a point over here and a point over here, I said, you shouldn't think of them as being close when I bend it this way, because they still have to stay in the page. But what if there were a little bridge connecting these otherwise distant locations? And that's the idea of a wormhole. So in this case, someone has created or spontaneously appeared a wormhole somewhere near Earth, and that allows us a little shortcut. We can just go through this tunnel, which is actually space, right? This is at one particular instant in time. We can go through there and take a shortcut and get to Vega in much less time. And that provides a lot of interesting questions. Again, here's the word hyperspace. Hyperspace is another word for nothing. Don't even imagine what's out there, because it's just not part of anything that anyone is asserting that exists. When, in science fiction films, when they say, we're gonna jump through hyperspace, nobody really knows what that means. Maybe it means you have some technology to create a wormhole that, connects two places by sort of bending space and causing them to be close to each other and making a little wormhole bridge. But then you wouldn't be going through hyperspace. You'd just be changing the shape of space. Yes, Joseph. Can what? Well, it could. I mean, we don't really have a good way of moving Earth around, but if it spontaneously happened to go down there. Now, I should say, wormholes, a lot of people have studied wormholes because they're, a great sort of theoretical interest, or also for entertainment purposes. But the idea is, if you create a wormhole like this, there's no problem with a wormhole existing at a certain period of time, but they close up incredibly fast. Like in 1 nanosecond, this thing would be unstable and it would break apart. So this would sort of split off from the part on the bottom into two, a stalactite and a stalagmite, that aren't connected, and they would sort of close up. So wormholes aren't easy. There's no way for a human being to get through it with the kind of matter we have in the universe. But people postulate these kinds of exotic kinds of matter that might be used to line the wormhole and therefore keep it stable, but that no properties of matter that anyone has discovered now would allow a wormhole to stay open long enough, even in principle, for anything to get through it. But it's an interesting idea that places in the universe that are far away might be closer than we think if there's a wormhole. Yeah.
Would the wormhole have like a gravitational force to it? Because if you're bending space-time, would things be
Yes, something's got to do that bending of space-time, and that bending of space-time is going to be caused by various forms of mass or energy that's doing that. So the wormhole itself, we think of a piece of space doesn't have energy that bends it, but something's got to be causing that bending, because the bending is always associated with the distribution of matter and energy in there. So there's here, I'm not showing anything that apparently is causing it. It looks like it just spontaneously developed, but in the theory of general relativity, there's got to be something associated with it, a matter distribution. Now, there's no problem with postulating that, hey, at some time, this is the shape of the universe. What happens as time goes forward? And the answer is, it just immediately closes up. So if you want it to stay there and to be able to travel through it, you've got to come up with some fanciful high tech or non-physical kinds of matter states. And I think that's it for this detour or byway into just picturing general relativity. I wanted you to come away with the idea of how you hear a lot about the curvature of space and curvature of space-time, but exactly how that mimics the effects of gravity. And so this was a compromise to allow us to visualize some of these effects, especially that we might be encountering in the movies that we're watching for philosophy, and some of the reading and some of the discussions that even come up in the forums. Any questions on that before we probably for the rest of the day just talk about a little bit of what happened in chapter 8 and going forward in the stuff you've been reading before we settle on chapter 13. Okay. Oh yeah, that's reminding me to talk about the word hyperspace. Okay, here's Merman's table of contents, just to sort of show where we're going. I mean, I really do hope that we get to chapter 17, which seems like at the rate we're going, this is absolutely impossible. But the idea is we have covered a lot of the stuff that is discussed, maybe in different words, in a different way that you're reading, in chapters 8, 9, and 10. 11 is a poem. You can read it. I don't think I had it in the reading responses, but you know, it's like a 4-page poem or something like that, or maybe 8 pages, I can't remember. This chapter 12, we're going to skip. You're welcome to read it. It's about how to, you know, something that's like a mechanical analog to what we're doing. I just found when I read it that it seemed excessively confusing of how to think about stuff, so feel free to skip it. We're not going to talk about it in class. The next section that we're going to thoroughly cover is chapter 13, the Lorentz transformation, and that's going to give us significantly more calculating power than we have right now, because we know if I want to compare the time interval between 2 events, as seen by one IRF and another IRF, the only easy way I have to do that is in the special case where one IRF has one clock that's present at both of the events. And then I could use the time dilation. And there's a similar kind of thing for length contraction. But I might want to know, hey, someone in one IRF observes some event over here, and then another event later over here. They're separated by 2 seconds. In a different IRF, what's the time separation? That's possible to do with the tools we have, but it's really almost impossible. It seems hard to even think about it. So this will allow us to do that rather easily. Just compare how things change in going from one IRF view to another. And then the really important chapters coming up here are what are the problems associated with going faster than the speed of light, and why naive ways that you might think about getting to a speed that's faster than the speed of light won't work. What's the consequences of faster than light signals or faster than light travels? You end up going backwards in time, and then someone could kill their grandmother before their mother was born, and all that kind of problematic stuff. The clock paradox is another name for the twin paradox. And even though I did talk about this briefly the last time we taught the course, I put it an extra paradox in the list there. And one of them is twin paradox redux, which is asking you to maybe think more deeply about the explanation I gave for how the twin paradox works only raises more questions if you think about it carefully. And so you might think about some of those questions, and I can help you think through that if you're someone who wants to address that. If no one chooses it, I may talk about it a little bit more at that point. And then probably the last thing we will talk about in the course is Minkowski diagrams. And you might think, oh, I already know all about space-time diagrams. Well, there's a lot we didn't discuss here, because the way we discussed them was almost like Newton could have drawn those same diagrams too. So what's special about special relativity? What's special about it is that events that are simultaneous for one IRF are not simultaneous for another, and we need to incorporate that that structure into our space-time diagrams, and that's when they become known as Minkowski diagrams. Okay, and well, certainly if we get there, I would love to talk about E equals mc squared and some ideas about that. We'll see if we have enough time. I don't want to rush other stuff in order to get there, but everybody likes to know about E equals mc squared. There is some stuff we can actually calculate with it, which is interesting. So that's where we're headed. So let's just hit some of the highlights in the remaining time we have today of the next couple of chapters. Objections and reflections. You know, I thought about putting some of your reading responses in here. Most people have said, oh, it's just a great summary. I love the summary, but there were no real questions associated with it. Here's a summary kind of all the effects in one slide. So I'm imagining here in IRF A, there's this thing that's, you know, built out of rigid rods with clocks at the corners, right? And of course, if it's at rest in IRF A, I'm going to make all those clocks be synchronized. That's the way we always do it. And let's imagine they have a certain tick length t0 for the clocks. Like that's how long a tick takes on this clock. 1 second takes 1 second, of course. And there's a certain length along this direction. You'll see why I don't care about the vertical length, because it's not going to be changed, because we're going to imagine what the view is from the point of view of someone who's moving to the right at a speed corresponding to gamma equals 2 relative to that. And down here, when we view that spaceship as at rest, of course, this whole thing is flying in the other direction at gamma equals 2. And we can see all of our effects in here. First of all, there's the length contraction, pretty obviously, right? It's contracted along the direction of motion. It's not contracted along the direction perpendicular to motion. That was one of our other rules, the non-exciting rule. The relativity of simultaneity along the direction of relative motion, the clocks are asynchronous when they're viewed as moving relative to that frame, right? But they are synchronous along the direction perpendicular to motion still. If they started out synchronous in this frame, they're still synchronous along this direction. See, they have the same reading there. It's only along the direction of motion that they become asynchronous. And the exact formula involves that LV over C squared thing, right? And furthermore, I couldn't really put this in as a picture, but the tick length actually increases. So these clocks are going to be going slowly compared to how they appeared to run up there. So that's kind of all 5 of those rules, or all 5 of the effects, visualized just in one figure. Nice summary. I believe this is from Merman. Merman talks about the corresponding Newtonian rules, which we should think of as they're incorrect, but they're certainly very useful, because a lot of things don't travel close to the speed of light. And so these are very close to being the same as the rules for special relativity when the relative speeds between different IRFs are really slow compared to the speed of light. So Newtonian rule 2 would say the time between ticks of a clock is the same for everybody. That's absolute or universal time. Newtonian rule 3 is a stick moving along its length has the same length for everyone. Newtonian rule 4, if clocks are synchronized in one frame, they're synchronized according to everyone in every frame. The obvious kind of stuff. And Merman has a nice discussion of why don't we notice that these are incorrect. I think, doesn't he talk about measuring the length of a plane that's going absurdly fast or something like that? And so if we imagine an object going absurdly fast, 30 kilometers per second, I mean, 1 second traveling 30 kilometers, that is just faster than anything, you know, we're close to having technology for doing. And yet, if we calculate this sort, you know, length contraction factor, look how close it is to 1. The first non-9 digit, 0.9999, is in, you know, is it the 9th position there after the decimal point? I'd have to count it up carefully. In any case, it's very close to 1. So we would say, you know, this thing moving would be length contracted to this fraction of its original length. Well, that's essentially the original length. We're not going to notice that kind of thing. Yet, subatomic particles do frequently travel at or close to the speed of light, and therefore the differences can be quite profound. If you're designing a particle accelerator, like the Large Hadron Collider, LHC in Europe, you're spinning those particles around and they're going close to the speed of light. That's important, because if you're slamming together a proton and an antiproton, which is one way they operate that collider, protons are fine. They're perfectly stable. They're happy to just sit there and not decay. But antiprotons do decay. And so if you want them to not decay, well, one way we've seen the same thing with muons, right? You can move them really fast to you, and then it seems like their half-life gets bigger and bigger, which means it takes longer and longer for them to decay, which means you have a long time to sort of speed them up before you collide them together without them decaying. So people at particle accelerators take advantage of that kind of stuff and rely on it all the time. They just naturally think in relativistic language. Nonetheless, Newtonian assumptions are built into our language, and we have to be careful about making statements about space and time. So we always have to ask, how and where were the measurements made? Who made them? And I think this was a big point in this chapter. Okay? Wow, that was fast. There's a chapter, but That chapter didn't really have anything new. It had some good points in it, but no new effects in it. Same thing here. I think from Merman's point of view, there is something new, but we did this discussion once before back in chapter 6, whenever we talked about the length contraction. Why, he says, my meter stick shrinks when I know his shrinks. How is that possible? It sounds like a logical contradiction. Here's the picture. We've shown this picture before, but just to remind you, because this is one of the things I want you to come away with from this course, is thinking, it sounds paradoxical. What's the picture? We can't just have one effect. If there were only meter sticks shrinking, we'd be in trouble, because there's no way that they can both shrink relative to each other. But if you combine that with the asynchrony of the clocks, the relativity of simultaneity, then let's imagine from A's point of view, here is A's meter stick sitting perfectly at rest, right? So we're imagining it from the rest point of view of that meter stick. And of course, we could attach some clocks to A's meter stick and we would make them synchronized, right? And let's imagine B zooming by at gamma equals 2, so it's going to be length contracted by a factor of 1/2. And here it is at some earlier time. At some later time, maybe it's zoomed farther. These clocks, of course, we're doing the IRFA point of view, so they all are still synchronous, and they've elapsed by a certain amount of time as they, so many nanoseconds as that thing is zooming by. If we want to understand how B could possibly see A's stick as being shorter, it just doesn't seem possible right here until you take the clocks into account. So let's attach some B clocks onto B. And of course, they're synchronized in B, but from A's point of view, which is what we're illustrating up here, B's clocks are asynchronous. This thing is moving to the right, so the back of the bus is over here, and that clock is ahead, right? This one's a little bit behind. This one's further behind. That's what we said. So let's imagine that it happens that this clock reads whatever upwards is, noon, when the back end passes the back end of A. It's got to read noon in any other IRF too. That's the invariance of coincidences. Well, if B is going to measure the length of A's meter stick, it's got to measure both ends at noon, right? If we measure this end, if the two ends line up at noon, I have to measure where this end is when this clock reads noon. So we shouldn't be measuring it right there. We have to wait till that later time. And here's a time where the middle clock has ticked forward a little bit as this thing has moved forward, and now it reads noon. And so B will say, we measured both ends of A's meter stick relative to ours at noon. The left end lined up with A's left end, and A's right end lined up with my 50 centimeter mark, and therefore A's stick is 50 centimeters long, despite appearances to the contrary here. And we can see that both those points of view make sense, but you have to combine relativity of simultaneity with the length contraction to see that. And similarly, I won't talk about this really here, but there's an absolutely symmetric point of view where B is at rest and A is moving like that. And so each one can see the other one as shorter. Okay, so here's a little summary from Merman. If you properly understand the relativity of simultaneity and careful measurements of the endpoints occur at the same time, there's absolutely no contradiction between I see your meter stick as being short, you see mine as being short. We have to remember when you measure something that's moving, you got to measure both ends at the same time if you want to know its length. Otherwise, you're not measuring the length. We saw that picture of the moving fish, where if you measure the front and the back during a time it's moving at different times, then no one would call that measuring the length. Okay, but the language used by different observers to describe the facts sounds very different, and I'm not going to talk much about these either, but Merman spends quite a bit of time in this chapter talking about what is B's statement of the facts, which sounds very different than A's statement of the facts, and it's probably not worth getting into here. He develops it quite a bit in there. They sound different, but the upshot, or what he concludes, is down here at the bottom. Therefore, the entire controversy between A and B is an argument not over facts, but over who uses the better language to describe these facts. So they're both describing the same underlying reality, but they sound very superficially different in the way they describe that reality. The correct answer is that either language gives us a clear and unambiguous description of the facts as long as it is specified which language is being used. So we didn't need to, back in this picture here, we never needed to consider the view from IRFB. We already understood how both of them could be seen just from the IRFA view. So as long as you understand whose point of view that is, you can explain how the other person would see it from their point of view, as long as you take all three of the effects into account. Wow, there's another chapter. This is going fast, so maybe we'll get to chapter 16 or 17 after all. It depends on how much stuff we go through quickly. Okay, this is the same thing for the time dilation. I changed it to she from he. I think Merman has it as why he says my clock runs slowly. But we've been talking about Alice and Bob, and it's 2020, so we may as well make it, you know, some gender parody there. Why she says my clock runs slowly when I know hers runs slowly. And, you know, we kind of already analyzed it in this particular kind of paradox, or I phrased it as a paradox. So the idea here was, remember, Einstein's standing here with his line of clocks, and we're taking the point of view of Einstein where he's at rest, and a clock flies by at gamma equals 2. And of course, we know if it's flying by at gamma equals 2, it ticks with, the ticks take twice as long, so it runs at half the speed. And that means by the time Einstein's clocks have ticked off 8 units of time, the flying clock has only ticked off 4 because its ticks are taking longer, and so on down the line. Here's where you might get superficially confused and think of this as paradoxical. Aha, there's no way the line of clocks can also run slowly when they're viewed as moving and still maintain these coincidences. This is a coincidence. The upper clock reads 8 when the lower one reads 16. The upper clock reads 12 when the lower one reads 24. How is it that from the point of view of the flying clock, if we take its IRF point of view, that it's going to see this one as going slowly, when these same coincidences have to happen in all IRFs? And the answer, of course, again, had to do with the relativity of simultaneity. From the point of view, so now we're taking the point of view of that formerly flying clock as being at rest and watching the platform move by, and we said, well, we know these clocks were, of course, synchronized in their rest frame. They're not synchronized here. They have some staggering of times as you go down the line at any instant in time. And therefore, notice that those coincidences, the 4 above and the 8 below, the 8 above and the 16 below, are still maintained in this picture. And yet, in between these two frames, these photographs here, 4 units of time have ticked off on Einstein's clock, and yet only 2 units of time have ticked off on the moving platform. So it is, in fact, going slowly. Einstein would say, look, each one of these clocks is going slowly. In the time my clock ticks off 4, each of these advances only by 2. And so there's I will admit that, you know, you really have to stretch your mind to put those two effects together and really see that they compensate for each other and allow both of them to see that they're moving slowly. It might be a little bit more obvious if we had not drawn just a single moving clock here, but a whole moving platform, and we would have seen immediately that those are asynchronous in this point of view, and it might have been easier to account for that. So the upshot is, if you properly understand the relativity of simultaneity and what it means for clock asynchronization, there's no contradiction in each measuring the other's clock as slower, even though it's, you know, a little bit mind-bending to put those effects together. One more thing that Merman mentions, I think this is the last thing besides some reading response things, so maybe this will just get us to the end of this chapter today. For a lot of these things we've been considering, it's not enough. You might think superficially that, oh, maybe I could understand this race somehow, that from A's point of view, if B is moving at half the speed of light, and here's a pulse of light that, of course, is moving at the speed of light, we already said, it seems impossible that from B's point of view that this would be moving ahead of it at the speed of light, because it seems like it would be moving ahead of it at half the speed of light. You might superficially think that, hey, if I just have the length contraction, we're good. because if you mess up the lengths the right way, this person B might have a different assessment of what this distance is. And isn't that enough to make up for it and just make everyone happy and see everyone see the speed of light going? Well, that may be true from one point of view, but then when you switch IRFs, you'll find the problem goes in the opposite direction. And so we actually need, the point of this discussion in Merman is that we need all three of these effects: length contraction, excuse me, time dilation, and the relativity of simultaneity. And they all work together if we want to have the principle of relativity hold and the principle of the constancy of the speed of light hold, okay? And I thought I put some reading response questions in here, but maybe I didn't click save afterwards, so we'll have to wait for those. There were at least one or two that I wanted to address there. And I think, even though we're a little bit before, is there any setup I want to do? I don't want to get into the derivation because it's complicated, even though I know you read about it. Yeah, let's just talk about for 2 minutes the setup of why we're doing this. There's a way to capture all of these rules, the length contraction, time dilation, relativity of simultaneity, and more in a mathematical way that puts them all together in a neat package. And it allows us to do a lot more than we can with those. These, as Merman emphasizes, very strongly, these can help to quickly solve a problem, but they can also obscure, because you have this nice piece of machinery that you just plug things into and it generates answers out of it. They can obscure what underlies why these effects are happening in the way they do, whereas you have a better sense of what's going on with the explanation if you explain in terms of these three kind of more physical effects to us. But it's widely used in physics classes, and it's convenient for complicated cases where intuition fails us. For example, I already mentioned if I have two events that occur at different locations and different times in one IRF, and I would like to know what's the time separation and the distance between those two events in another IRF, but neither one is present at both events. This formalism, the Lorentz transformation, will allow us to answer those more general questions. And so what we're going to do is imagine two different IRFs. Here's one F, and I'm imagining it that F is at rest from this point of view, so this is F's rest frame. Here's a meter stick that's at rest in F. And the relative motion between these frames is going to be along the horizontal direction. Here's a perpendicular meter stick. We'll call that the y-axis. So these are moving relative to each other along the x direction. And there are a bunch of clocks stuck along these meter sticks. So we have local observers reading those clocks. And we're going to consider another inertial reference frame, F prime. And we're going to, of course, F prime might have chosen to have his or her meter sticks oriented in a really oblique, funky way relative to the first one. And the clocks may not correspond at all to the clocks in A. But we're not going to assume that, because you can describe the transformation that way, but it makes it horrendously complicated. It's much simplified if we make the following assumptions. In each frame, its clocks, we're going to assume, are synchronized, as always. So in the rest IRF, we'll assume, like in F's rest IRF, all these clocks should be synchronized. Now, if F prime is moving in this picture, I expect these clocks to be synchronized, but these ones along here to be asynchronous, because that's going to make them synchronous in its own rest frame, which every sane person is going to want. We're going to imagine that the three coordinate axes overlap momentarily. In other words, these two frames are moving relative to each other, but there's an instant in time, according to F. When we say an instant in time, we have to say according to whom? According to F, where the X, Y, and Z axes all coincide with each other. So the origins pass each other. Don't worry about the practicality of having meter sticks pass through each other. They're just imaginary meter sticks. And we're going to make that time at which they coincide in F, we're going to call that t equals 0 at F. So when F prime is moving along and it lines up with it, that's going to define t equals 0. And t, when I say t, I'm going to associate that with F. T prime is going to be the time as assessed by F prime. That's how we'll keep sense of the coordinates. So At this time, F, which is the blue one, you can't see it because the red one's on top, all the clocks would read 0 on F's clocks. Also, we're going to decide, because we don't want F prime's clocks to be totally randomly set compared to F's, we're going to say, let's assume when the two axes, or all three axes coincide at that instant in time, we can all agree on that because that's a coincidence of two events at some particular location. Since F's clock is going to read 0, we're just going to say, oh, F prime also has a clock set so that it reads 0 there at that instant in time, the one we're showing right here. So F prime's clock here would read 0, and that means this one would read 0, 0, 0. These ones over here aren't going to read 0 because they're moving, so they're going to be asynchronous as they go along. And the idea is, suppose some event happens. Here's an event that happens as F prime is zooming in this direction, F is sitting there, right? They're each going to assess different coordinates for it, right? F, the blue frame, is going to say, oh, it happened at this bigger x value on my axis, whereas F prime is going to say, oh, no, it happened at a smaller x value. They'll agree on the y coordinate if they set up their axes this way, because there's no shrinking or movement along that direction, but they'll disagree about the x coordinates. They're also going to disagree about the time that it happened, even given how carefully we set the clocks at the origin matching as t equals 0 and t prime equals 0. So the goal is, and this is where we'll stop today, yes, they're going to agree on their assessment. If we align up, the relative motion is only along x, and we agreed that the axes line up at a certain instant in time, they'll agree on the y and z coordinates of any event. But they're going to disagree maybe on the x coordinates and the t coordinates. So how can we compute, if we know the x, y, z, and t coordinates that F reads for this event, how can we compute in terms of those what x prime and t prime are? So we need to, this is a function F, and it's a function of these 4 variables. G is a function of these 4 variables, and it's our task. And as you've seen from the reading that you did for today, it's not an easy task. It's the most difficult derivation that we've encountered so far. That's okay, we'll go through it logically. You're not responsible for knowing it, but I still want to have you see that each step is no great leap of faith, but it is hard to swallow the whole thing in one sitting. Okay, let's stop there. We'll get into the derivation tomorrow. And now, either if you haven't turned in your homework,